CURE.
The abbreviation, sir.
Sorry?
The abbreviation.
Sorry?
The abbreviation.
It's an abbreviation, yeah, the clustering using representative points. I got that. Huh? What was that? No. Represent, just use the first two letters of representative. Representatives. Okay. CURE sounds bad, right? CURE sounds easy, nice and clustering using representatives, right? Okay, fine. So with CURE again was touted as a an algorithm for handling really large data sets. Right, CURE again is an algorithm for handling large data sets. So the way you do this here, unlike Birch where you actually go through all the data points, okay. So in CURE what you do is you sample a large fraction of the data, okay, as large a fraction as would fit in your memory comfortably, okay. Sample a large fraction of the data and then you do some kind of clustering on that, okay. Right. So what you do in the clustering, then you after you have done your clustering, right. So you start off with some initial clustering of the data, right. Then what you do is, let us say I have something like this, right. Some kind of weird shaped data like this, right. Once I have done some kind of clustering, so I will take the center, okay, I will take the data point farthest away from the center, right. So this is, let us say this is a cluster, I take the data point farthest away from the center, let us say that is it, okay. Next I take the data point that is farthest away from this data point, say that, then I take a data point that is farthest away from, roughly, do not worry, I am not measuring it with a scale or anything, right. I will take the data point that is farthest away from both of them put together, right. So I compute the distance from both and then add it up and then let us say that one, and then I figure out one more if I need one more, right. I will take that one, right. So now I will take these as my maybe not that one, that one. I will take these as my representative points for the cluster, right. So a data point gets assigned to that cluster which has a closest representative point. Basically I am looking at the boundary points, right. So I am looking at the representatives or things that delineate the boundary of my cluster, right. I do not take too many points, right. I take some number of representatives like 3 or 4 representative points, right, or say 10 representative points, so that they do not completely trace out the boundary, but they give me some kind of idea of what the boundary is, okay. So this is why representatives.
Then what do we do after we find the representative?
I reassign the clusters, I reassign the data points, right. So I have some clusters now, I find the representative points, I find the representative points for this cluster, I find it for this cluster. Now I reassign the data points to clusters. So a point goes to that cluster which whose representative point is closest. Earlier we used to reassign them to the closest centroid. Now I will reassign them to the closest representative point.
So now there are 4 points for
no, for each cluster I will have 4 points, right. For each cluster I will have 4 points. So what I will do now is I will forget the cluster memberships, right. This is just like how k-means works, right. So k-means, what will I do? I will reassign a data point to the closest centroid. Now I will reassign the data point to the cluster that has the closest representative point, okay. Initial, whatever, the whole thing is done out of a set of samples, samples I drew from the data.
So rather than measuring one centroid, you are measuring 4 points for
4
each.
points for each cluster.
If I look at representative points, still we reassign 2 clusters among the sample.
Yes, among the sample points, but just one thing I forgot about the representative points. One point I forgot about the representative points, apologize. So once you identify these guys, right, so you don't take them as your representative points because they will become too susceptible to outliers, okay. You do what is called shrinking, right. You move them some fraction alpha towards the centroids, right. So I find the points at the boundaries, right, and then I shrink them a little bit towards the center, right, so that I do not get too influenced by the outliers, and the shrinking is done by a fraction of the distance to the centroid, so that the farther away you are from the centroid, so the greater the shrinkage. Okay, so this is how you find the representative points, and once you find the representative points, you go ahead and keep doing this on the same sample, right. So the idea of taking this sample is small enough to fit in your memory, right, so that I do not have to go back to the disk to read the data for the second iteration.
But it does not assign some a data point that's not in cluster to some.
We still a couple of stages to go. Okay, this is the first stage of cure. I draw a sample, okay, I cluster using these representative points. Okay, so remember that the sample I hope is representative of the whole data set, but it might not be. Right, I have taken some as large a sample as I can from the data, right, into my memory, and then I do this clustering around representative points, right. Is it the clustering, the representation based clustering is clear, right. Just like k-means, instead of assigning it to the data point with the closest centroid, I assign it to the data point with the closest representative.
The number of representative points.
It's a parameter, yeah, it's m. Some m you choose. Like in this case, we chose it to be 4, right? Yeah.
How do you choose the initial representatives?
What's it?
How do you choose the initial representatives?
That's what I said. You start off with an arbitrary clustering. Okay, start off with some arbitrary clustering. Okay, and then you start. You pick representatives. Find the centroid of that clusters that you have, right? And then go to the corners, shrink them. Right, do not forget the shrinking step, shrink them and then you get your representatives, right. So just like the centroids are not real data points, the representatives also need not be real data points, okay, because once you shrink them they are no longer, so when you find them they are real data points, then you shrink them then they are gone, right, they are no longer real data points. Okay, now you get m such.
I will reassign all the data points or the points in the sample.
Sorry?
I will reassign all the data points or the points in the sample
Only in the sample. So when I am doing the clustering I am not worried about anything else that I haven't sampled, right. So now what I do is I keep doing this until I have converged to some clustering, right. Once I have converged to some clustering, okay, what I will do is I will remember those representative points. Suppose I have k clusters, I will have m times k points, right. I will remember those k representative points, I will forget everything else, right. Now I will pick another sample from the data, I will repeat this. In fact, the recommended way to do this is to partition the data initially randomly into some large number of bins, like say k bins, right, partition the data randomly into k bins and then run cure in parallel on each one of those k bins. So if you have a lot of machines, so what you can do is you can take your entire data set, okay, this is not meant to be a geometric representation of the data, right. So no, when I say I am going to divide it into parts, I am not saying take data that belong to one part of the input space and assign it to, I do not know this, right, I just randomly split the data, right, and say that okay, here there are 5 bins, okay, and in each bin I will run cure independently, right, and what will I end up with? Some mk points for each of these bins. Now what will I do is I will throw in all the mk points into a single clustering problem and run cure on those mk, whatever, 5 times mk points again.
And then the answer will be?
Again you will get a set of representative points, right, for each cluster you will get a set of representative points. Then I will go back and assign each data point to the cluster which has the closest representative point, right, and on each part I run cure, right, I will end up with some clusters, right, and for each clusters I will have a set of m representative points. Let us say I end up with k clusters in all of them, okay, I will a priori define k, right, I will end up with k clusters in all of them, right, and so there will be some mk points from here, where m is a parameter that I have chosen already, which is the number of representative points, let us say 4. Now what is happening is I have a small fraction, right. For each cluster I am going to have 4 points, right. So that is a small number, right. My number of data points will be very large, the number of clusters will be small, right. I will have 4 times the number of clusters, that is a small number, right. I have now 5 such divisions, so I will have 5 times m times k points.
So what is the K over here?
K is the number of clusters,
K clusters.
k clusters,
K clusters. That's defined before.
just like k means, yeah, you define k a priori, right. Right. So, but the point here is at every point, at no point am I looking at a larger clustering problem, right. So, I have split the data, right. So, I am looking at some fraction of the data, 1/5 of the data or 1/10 of the data, and that is the largest data set size I am going to look at. This is why CURE is a algorithm for handling very large data. So, I can take a very large data, I can split it up 10 ways, I can split it up 15 ways, 20 ways, and I will do each one of these clusterings. So, if I am looking for 100 clusters and 4 representative points, so that is basically 400 points returned from each one of these clusterings, right. And then what I do is if I have 5 of these, right. So, I basically end up with 2000 points, right. So, I have 100 clusters, 4 representative points per cluster, right, and 5 such problems I have solved. So, I end up with 2000 points, very small number, right. So, I go and run CURE on that again, right. Again I will get 100 clusters on this 2000 points, right. Bad idea. 100 clusters on 2000 points is a bad idea. You basically end up with 20 points per cluster. So, what you should typically be doing is whatever final clustering you want to end up with, this should be much larger than that. This k that you use here, suppose I want to end up with 30 clusters, then I can use 100 clusters. Suppose I want to end up with 100 clusters, I better end up using a larger number, 200 clusters or something. Okay, so that I will have enough data points to cluster finally, right, and then I do the clustering. Suppose I end up with 30 clusters, each will have 4 representative points. I will pick those 4 representative points. I will do another scan through the entire data set. Right. How many scans I have done through the entire data set so far? 1. So far I have done only 1. When did I do the scan? To do the partitioning, right. So, I did the scan once to do the partitioning, right. The second time I do the scan, I will have m representative points from 30 clusters, right. I will go and assign the data point to the cluster that is the closest representative point, right. So, at every point I do not solve a problem that is larger than what I put into this one partition, right. This allows me to do these things very rapidly, and if I have multiple processors that can run, right, I can do this in parallel. This stage can be done in parallel, and whatever cluster representatives it return, and then I do a second round of clustering. So, CURE is, if you do the implementation correctly, it is rather fast. Okay. And another nice thing about CURE is that because I am doing this clustering around representative points, I am not really limited to looking at convex clusters like I have with k-means, right. So, k-means, if I have 2 centroids, right. So, basically this will be the separating line. If I have 3 or 4 centroids, I will basically be looking at some kind of convex shape around the centroid, right. But if I have, since I have multiple representative points, I can actually have non-convex shapes also.
What is the disadvantage?
Disadvantage of using non-convex shapes?
No, it's CURE.
This is overhead, right. So, if the data is small, you really do not want to get into the CURE kind of a setup, right, because the overhead is large, and you have to maintain so many representative points, right. So, every time finding the representative points involves you getting the centroid and doing this computation to go to the edges and then shrinking them, right. So, it is additional overhead. That k means you just find the centroids and you just move on. Here you have to do additional computation. So, that is the overhead. Okay, good. So, any questions on this?
Shouldn't we include the centroid as a representative?
No. No, it usually defeats the purpose. Right? I am assigning it to the data point that has the closest representative point, right. So, the centroid will be anyway surrounded by the representative points I am taking. So, it will anyway end up going to the same. There might be a small change here and there, but people typically do not include the centroid in the representation.
in the sense that we have to now decide on 2 parameters a priori.
Yes, but you get some advantages for that, right? It runs on large data sets. If you just stop and think about it, you could even do k-means this way and claim it runs on large data sets, right? So the second thing is you can get non-convex clusters. So if you have funky shapes, funny shaped clusters, then you get those.
Points from a single cluster are never broken apart, right?
In the sense, representative points are not real data points. They are fictional points like centroids. So when I do the reassignment of points to clusters, representative points never get reassigned. I mean, they are not points at all. Right? Remember, I told you go to the edge, you find real points, and then you shrink it by a factor alpha towards the center. So that's another parameter you have to select. So 3 parameters. Right? You shrink it by some factor towards the center. So therefore, they are not real points. Just like the centroid doesn't really get reassigned, neither do the representative points.
So in this case also, if you take something like a meroid, then will it perform better in the sense that more robustness to outliers?
So whole point of doing the shrinkage was the robustness to outliers, right? Yeah, you could think of using the meroid, yeah, more computation. Right? Yeah.
For the sampling too, we could do sampling without replacement.
What's happening?
To pick the
Yeah, we do
initial
without
data.
replacement. That's why I showed the partitioning there. We typically sample without replacement in Cure.
So we could do with replacement as well.
You could. You could. I'm not saying you can't. I mean, see, the point is for every variant that you propose, you have to either convince me empirically that your variant is better, or convince me theoretically that your variant is better. No, that's how people generate papers, right? And yeah, so you have to stop and think, what is it that it buys you? You know, is there some kind of statistical parameter that will become better by sampling with replacement versus sampling without replacement? And for example, will you get more stable cluster estimates if you sample with replacement? Right. So regardless of how I split the samples, right? So if you say that I'll get the same cluster centroids, maybe then that's a valid thing to do, right? If you can't show anything like that, then it's not clear, right? So the thing with which has more overhead, sampling with replacement or sampling without replacement? Sampling without replacement has more overhead. Really?
Kind of store.
With replacement has less overhead. If you are only sampling, okay. If I am interested in partitioning the data, I can just look at some random permutation of the indices, right, and then just chop the data at some points, right. So that is like sampling with sampling without replacement, but I have exhausted the entire sample space. So if I am going to do that for sure, right, then I can do it efficiently, right. Then that actually has lesser overhead than sampling with replacement, right. Why does sampling with replacement have lesser overhead than without replacement? When I do it with replacement, I don't have to keep track of what I have already sampled. If I am doing it without replacement, I actually have to remove it, or I will have to have some bit that's set there that says, hey, this thing has been visited. So how do I change my sampling distribution so that I avoid those data points which I have already sampled?
Partitioning is one of the way.
We just evenly partition. Evenly partition.
Yeah.
It's not that much hard.
What's that?
It's not that much hard to sample without.
Yeah, you can pre-roll your sampling. Yeah. So if you are going to just sample one at a time, then it is a problem, right? If you can pre-roll your sampling, that's essentially what both of you are saying. Right? You can. What I am saying is you a priori generate all the random seeds you want, right? Just do the permutation, right? And then just keep popping off the whatever is the ID at the topmost. Right? So that's a way of implementing it. That can be pretty efficient. Yeah.